Swayam Prabha. Digital India. Educated India.
Okay, welcome everyone. So today what I will talk about is a little bit more about constraint qualifications, and then we will move on to the theory of duality for convex optimization. Now you will recall that I had told you about what is in an abstract sense what is called a constraint qualification. So a constraint qualification. If you recall, I had mentioned that we say that a constraint qualification holds if the tangent cone can be described in terms of the constraint, in terms of the gradients of the constraint. So let us say, suppose so to describe this properly, let us take let S be the set Gi of x less than equal to 0 for all I from 1 to m. If you remember, A of x star was what we call the active set. It is those I in 1 to m such that Gi of at x star is equal to 0, and we say that a constraint qualification holds if the tangent cone with respect to the set S evaluated at x star is equal to the set of D's such that, so these GIs, remember, are functions from Rn to R. So S itself is a subset of Rn. So we say that the constraint qualification holds if the tangent cone can be written in this, it can be expressed in this sort of form. It is all these such that the gradient of Gi transpose D is less than equal to 0 for all I belonging to the active set. Right. So if if this holds, then we say that that a constraint qualification holds. Now we do not I also alluded to you that one way by which one condition that ensures that this holds, right, the one condition that ensures that this holds was what was called the linear independence condition. So it said that if these gradients, so the linear independence constraint qualification was one such constraint qualification. Linear independence constraint qualification was, it simply said that all these gradients at star, these are linearly independent. Now, if these are linearly independent, then that guaranteed us equality in this relation. So then essentially we could characterize the tangent cone as given by this particular set of inequalities. Now, what I'll mention to you now are some more constraint qualifications. So some of these have names, some of these are have been just referred to in the literature by kind of directly. So here's one constraint qualification. Okay. So suppose we are referring to some x star in S, and suppose, so we are I am here in this in these constraint qualifications, I am going to be referring to S in this sort of form, okay, in the form that it's all those x such that gi of x is less than equal to 0. So this gives us constraint qualifications for sets that are described completely by inequality constraints, but then you can always extend it directly to those which have equality constraints by posing the equality as two opposing inequalities. Okay. So suppose x star is in S, and suppose there exists an H star in Rn such that for each I in the active set, we either have gradient of I of gradient of gi transpose d is less than 0, strictly less than 0, or gradient of gi evaluated at x star transpose d is equal to 0, and gi don't need the bracket here, and gi is affine. Okay. Then we can then the constraint qualification is satisfied. Constraint qualification holds. So in short, this here what I have written here is a, you can say, is a sufficient condition for a constraint qualification to hold. So this sufficient condition for CQ to hold. Now you can make this. So what does this say? This says that oh, my mistake here. I shouldn't say. Let me erase this. My mistake here in the notation. Instead of H star, let me write D. Let me write D. So if you can find a direction D such that for every constraint in that direction if you move in that direction, for every constraint that's active, and from that if you move in that direction for each constraint you become strictly feasible, or you remain on the constraint but then the constraint is affine. Okay. In that case we say that then from there it would follow that there is equality here, that the constraint qualification holds, right. Okay. Now there is a somewhat longish proof for this. I am going to skip the proof. If you want to look up the proof, you can look up the notes of Praveen Varaya on the internet. So here is another constraint qualification. Actually, this one is very popular. It's a very popular constraint qualification, and it comes out as a weakening of CQ1, right. So let me mention this to you. So once again, suppose I should be more clearer here. CQ, then the CQ holds at x star. Okay. Suppose x star is in S, and suppose there exists a direction D sorry, I do not need the direction D here, my mistake. Suppose X star is in S, okay, and suppose there exists an X hat, okay, in Rn such that the following holds, such that for each I in the active set A of X star, either Gi of X star is strictly less than 0 and Gi is convex. Okay. So, this for us are all, and also in C1. Okay. I did not mention it, but these functions are all differentiable functions, otherwise I will not be able to take derivatives here. Yeah. So, these are so this is strictly less than 0 and Gi is a convex function, or Gi of X star, sorry, this is not X star, sorry, this is X hat, my mistake today. So, and Gi of X hat is less than equal to 0 and Gi is affine. Okay. So, suppose you can find a point x hat here, a point x hat like this, an x hat in Rn, such that for each constraint in the active set, either the constraint holds strictly at x hat. Okay. Either the constraint holds strictly at x hat and the constraint itself is a convex constraint, or the constraint just simply holds, it is Gi of X hat less than equal to 0 and the constraint is affine. Okay. In other words, for affine constraints, all you are asking for is feasibility, and for convex constraints you are asking for strict feasibility. Okay. For convex constraints you are asking for strict feasibility. Okay. So, naturally an affine constraint is also convex constraint. So, so those that are so this one is to be applied, can be applied only to those constraints that are non-affine and yet convex. Okay. So, for this what we are asking for is strictly feasible. So, this sort of point, this point x hat is what is called a Slater point, and I will make a mention of it again. It comes up in a very important way later also. It is what is called a Slater point. So, x hat is what is called a Slater point, okay. And this condition itself is sometimes referred to as the Slater condition, okay, that there exists such a point. Now, there is a weaker version of this where you do not ask for the trouble with the way this way of writing constraint qualifications is that it asks us to check this for every I in the active set. A much easier thing to do is not bother about the active set at all, and to check that this holds for all I. Okay, and so sometimes when we refer to a Slater point, we refer to that to a point where these hold not just for I in a certain active set, but rather for all I. So, so essentially what it refers to is that your the existence of in that case what this is referring to is that your the feasible region S is such that there is there is a point that is in the interior of all the convex constraints and is feasible for all the affine constraints. So, these points here which satisfy the convex constraints with strictly this point here, where all the convex constraints are satisfied strictly, that sort of point is in the interior of all the convex constraints, and this ensures that it satisfies all the affine constraints. So, these two put together is effectively saying that you have a point that is in a strictly in the interior of the convex constraints and satisfying the affine constraint. Now, what does this have to do with the constraint qualification? Well, you can actually check once. I will just mention a hint here. The hint is to check try hint is try D equal to x hat minus x star in constraint qualification 1. Okay, in constraint qualification 1, you try out D as x hat minus x star, use the fact that G is convex and G is differentiable, etc., and that should bring you back to something like this, right. Okay, so I won't say more than that. Okay, I didn't complete my sentence here, so let me do that. Okay, so with these constraint qualifications done, we will now move on to the study of duality in convex optimization. Okay, so here is my optimization problem. So minimize f of x subject to g I of x less than equal to 0 and for all I equal to 1 to m. And although we are talking of convex optimization, let me just write this out first for the moment in a little bit in a general sort of way. So, with Hj of x equal to 0. So, in a convex optimization problem, obviously these would be linear, but let this issue come up when we actually need it. Now, if you recall, I had defined this function called the Lagrangian function. So, I had defined it as this summation lambda I g I of x, I going from 1 to m plus summation theta j h j of x, j going from 1 to p, right. Okay. So, this was what was called the Lagrangian function. And then now let me define the following other function. This function is d, which is a function of just lambda and theta. This d is simply the infimum of the Lagrangian over the entire space, infimum over x for a function for a fixed lambda and theta over the entire space. Now, this function is what's called, there is a name for this is called the dual function. Now, there is a reason why it is called a dual function, because you will soon see that it is actually related in a very close way to duality itself. So, the problem of the dual problem and so on comes up exactly from there. Now, before we actually go a little deeper into this, so is there something that can be noticed directly first? So, here are a couple of things that you should note. Okay. First is that d is a function which is a pointwise minimum of linear functions. What does that mean? So, if you look at the if you look at the Lagrangian as a function of, if you look at the Lagrangian function as a function of just lambda and theta, then it is actually linear in lambda and theta. And what you are doing in this definition here is taking the minimum of this sort of linear function over a third variable x. So, you have if you look at this as functions of lambda and theta, you have in fact a family of linear functions of lambda and theta, and what you are doing is taking for each lambda and theta the least of those. Now, what sort of a function would result from this? A pointwise infimum of linear functions would end up becoming actually so that actually becomes necessarily a concave function. Okay, so this is something you can prove for yourself, that D is a concave function. It is a concave function of lambda and theta. And now, this fact does not require, this does not require f, g, etc., f, g, h to be convex. So, the problem does not need to be a convex optimization. The fact that D is always a concave function is holds for any optimization problem like this. Okay. So, as a consequence, what we can say is, if I suppose I pose this following other type of problem, which is, suppose I say, look at this problem where I am looking to maximize with subject to lambda greater than equal to 0 and all theta, the function d of lambda comma theta. This sort of a problem is therefore a convex optimization problem. This sort of problem is a convex optimization problem. And why is that the case? The reason for that is because its objective is concave and you are maximizing the objective. So, effectively it is equivalent to minimizing the negative of D. So, if you are minimizing the negative of D, that would be a convex, minimizing a convex function over a convex feasible region, which is just lambda greater than equal to 0 and theta unconstrained, or in short theta in RP. Right. So, this is always a convex optimization problem. This problem is what let me give it a name, it is what is called the dual problem, and you will soon see that this is in fact nothing but the dual problem that you have encountered, the same as the dual problem that you have encountered as part of your study in linear programming. All right. Okay. So, well, if this is supposed to be the dual problem, then where are the relations of duality, which is strong duality and which is strong duality and weak duality. So, let us first look at weak duality. Strong duality is where where we will spend most of our time subsequently. So,